Hi, everybody. Good afternoon. My name is Andy Hawk, and I am the Vice President and Head of Product here at Cerebras Systems. So you've been hearing from some of my teammates earlier today. I see some familiar names on the chat, so nice to see many of you again. And for the rest of you, I look forward to the opportunity to work together between our teams. Interestingly enough, I just came from another call about very large-scale AI models for science. It seems that this is a hot topic right now, which makes perfect sense. As Richard said at the beginning of this call, we see really revolutionary potential of large-scale AI models for science. But some of the common challenges in building and iterating upon such models is data, ML methods, and of course, being able to readily distribute such large AI models over large systems and then train them quickly such that as a part of a scientific enterprise, our users can quickly ideate and test hypotheses and effectively test more ideas per unit time. And many of us at Cerebras actually come from scientific backgrounds. My own background is in geophysics and space physics and a little bit of molecular biology. So I think we understand this need to be able to quickly iterate, even at very large scale. And although much of our focus as a company is in the commercial world, we really built the systems that we built in some sense as an observatory to develop the next generation of large-scale AI models, including those for science. And so we're really excited to be here today and tell you a little bit more about our systems, as you heard in the previous sections, and now some example use cases, just to give you an idea of the kind of value and applications other parts of our community have brought to life on our machine. So if we could, let's jump to the next slide and we'll get right into it. So you heard in the previous sections about our systems and software and saw some of the performance attributes of the machine. So how does all this translate into value for your research, right? First, obviously, the ability to train large models in days or weeks instead of weeks or months, accelerate research and development of production models, as well as production model fine-tuning or retraining, allowing you to iterate more quickly, even at scale. But the ability to iterate quickly at scale isn't just about compute. It's also, of course, about software and setup time. And our system, by virtue of its large-scale SRAM and purpose-built Memory X architecture, can run even the largest models today on a single system. And as you saw in the last section, also scale up performance nearly linearly as we scale out the number of nodes. So the ability to set up and scale in just a few hours with a few lines of codes is a significant contributor to the ability to get to work quickly and iterate quickly. Save yourselves weeks or months on cluster engineering, allowing you and your teams to focus instead on AI application value in the domain science. And last but not least, with massive compute volume comes the ability to work with much, much larger data sets. That might be necessary, either unimodal or multimodal data sets, including language and other sequences, and eventually building into multimodal data sets. And a couple of examples just at the right to illustrate the value of performance and scaling on Cerebras machines. One of the earliest projects that we engaged on was a project called CANDLE, or Cancer Deep Learning Experiment at ANL. And there, as you can see, a quote from Rick, some of our earliest work produced orders of magnitude acceleration on a first generation CS machine over GPUs for one of their cancer models, a part of the CANDLE project. And on the bottom right, we've also worked with many commercial customers that are building AI models for scientific development. Here, AstraZeneca, the biomedical and pharmaceutical giant, was using our machine to train large language models on scientific literature. And as you can see from the quote there, training a large model took them just about 2 days on a first generation Cerebras machine that was taking them 2 weeks to run on a cluster of GPUs. If we jump into the next slide, I have a few other cool examples, but First, I wanted to share some interesting recent results that go to the point that I was mentioning before about Cerebras building our machines and our team to really accelerate the next generation of AI models. This is a chart that was part of a report called the State of AI report, which is a regular analyst report on AI technologies and markets. And what the chart shows is the number of citations in AI research papers divided up by the company of various AI chip and system startups. You can see in there, Habana, GraphCore, Cerebras, SambaNova, and Cambricon. And one of the things that we were most proud of at Cerebras over the past year is that we've developed our software and systems significantly and sufficiently such that more and more researchers are starting to use our machine to really not just train existing models, but push the envelope of what's possible in new models. And you can see over the year 2022 to 2023, the citation of Cerebras systems cited in cutting edge AI research leapt up, and we're looking forward to continuing that trend. A couple of specific use cases. I think you may be already familiar with this one if you're at Argonne or part of the Argonne National Labs ecosystem, but we worked significantly with a team at Argonne over the past year or two on bringing up and training very large GPT models for COVID sequence generation. The purpose of the model is really to understand the dynamics of the COVID genome and to eventually potentially predict likely mutation variants of the genome. This is really, really exciting work. And at the end of the day, it fundamentally boils down to being able to train multiple large GPT models on very large, long sequence length data. So the team here, and the reference publication is down at the bottom. The team here trained several large GPT models ranging from 250 million parameters to 25 billion parameters on full sequence length COVID genome data, so MSL 10,240 data. The team trained them on both a cluster of 16 Cerebras systems, that Andromeda cluster that Nick mentioned earlier, and also on ANL's own 512 A100 GPU cluster. And what you can see in the chart on the right, we have samples per second in terms of training throughput as a function of model, the 250 million, 2.5 billion, and 25 billion parameter model. And the bars on the left show what's described in text on the far left, that is training the 250 million parameter model, same data set. The cluster of 16 CS2s delivered the effective throughput 832 times faster than an A100. That assumes linear scaling of a GPU cluster, but as you know, is very difficult on other systems to get linear scaling of throughput at such a large cluster scale, a large number of devices. So in reality, if you wanted to achieve the same throughput that we got on a 16 CS2 cluster on a GPU cluster, you probably need far more GPUs. So this is a really exciting performance result, right? Because it allowed the team to iterate more quickly. But we were also able to readily train models on this system at even larger size with long sequence length data. So you can see there in the chart, we also have throughput measurements on 2.5 and 25 billion parameter models. The team wasn't able to replicate those runs with the same sequence length data on GPUs at the time because they ran into some memory issues associated with attention computation. If you go to the next slide, we were thrilled to be a part of this team as it relates to new scientific discovery. Our team was a co-author on the paper, which is shown here, GenLSMs, genome scale language models that reveal SARS-CoV-2 evolutionary dynamics. We submitted and were selected as a Gordon Bell Prize, special prize recipient for COVID-19 research. I wanted to also call out this point about being able to iterate with large models at scale. In the second quote that starts to enable training of larger models on full sequence length tokens, we leveraged accelerators like the Cerebras CS2 and allowed them to obtain Gen SLMs that converge in less than a day. So I think it's exactly this kind of work that we see as an indicator of the future, and also a good illustration of the value of our machine. Alfred, that's a good question. So Alfred asked about why does throughput go down with the number of parameters? Basically, the overall training compute requirement goes up with parameter count. And so therefore, the time it takes for each token to be computed across every layer of the model also goes up. So that's why you see effective throughput really on all systems would go down as a function of model size. And we can go ahead and jump to the next slide. This is another good example. It's an earlier one done with Cerebras team as well as our collaborators at GlaxoSmithKline. So GlaxoSmithKline is building large language models for multiple scientific applications, from knowledge discovery to the development of new genetic medicines. The paper shown here at the right and referenced at the bottom right is an illustration of the latter. It's called Epigenomic Language Models Powered by Cerebras. This is an early publication from their team. The underlying work is ongoing, where they pre-trained a BERT-style language model on both DNA sequence data as well as cellular epigenetic state data represented as a sequence for cell type specific transcription factor binding prediction. The fine-tuned model came in third overall on a transcription factor binding prediction challenge called ENCODE DREAM, and actually beat state-of-the-art performance on a number of downstream tasks associated with transcription factor binding. So the model worked and exceeded state-of-the-art on multiple dimensions. But moreover, on the system front, we see those two quotes on the bottom left once again talk about the sort of the value of performance at scale for scientific research. The model that they trained then on a first generation Cerebras machine, a CS1, was trained in 2.5 days and would have taken them more than 24 days, so more than 10 times as long on a GPU cluster that they had with 16 nodes. And so here, obviously, we can get excited about the performance result from a computational standpoint, but what I think is really relevant to science is that the training speed up, as they say, afforded by the Cerebras system allowed them to explore architecture variations, tokenization schemes, and hyperparameter settings in a way that would have been prohibitively time and resource intensive on a traditional cluster. So here it wasn't just going faster for the sake of going faster to achieve, say, a better benchmark, but it was going faster so that their team could iterate more quickly and fundamentally build a new model. I think you'll see there's going to be much more good work from this team coming soon. Their work and their usage of systems has continued with our team for some time. And the next slide. This is an interesting example. At Cerebras, of course, we're building our machines with an eye on accelerating large-scale artificial intelligence. But in the traditional scientific HPC community, there's also growing interest in using AI models to accelerate fundamental science and high-performance computing. Whether building AI models as surrogates for underlying physical, chemical, biological processes, or using AI models alongside traditional simulations to accelerate overall time to solution for a complex modeling and simulation routine. This slide is an example of the latter that we worked on together with researchers at, once again, A&L in late 2021 and early 2022. This is an example where the A&L team, along with Cerebras collaborators, was using a large GPU cluster for traditional molecular dynamics simulations of the SARS-CoV-2 spike protein, and then streaming the state and trajectory of those molecular dynamics simulations from the GPU cluster out to a Cerebras CS1 accelerator, and then doing online training on the CS1 to learn the embedding state and use the output from the CS1 to identify outliers and inform the next steps in the molecular dynamics simulation. So what you can see then on the right is a comparison of overall time to solution for an 8-hour experiment, comparing the molecular dynamics solution time to equilibrium on a cluster of A100s only, GPU only, versus a cluster of A100s plus Cerebras in the loop. And what you can see is that the results were in fact better in the 8-hour simulation with the CS1 in the loop. So basically accelerating time to an equilibrium solution by using an AI accelerator in the loop with a traditional HPC-MD engine. And this, in the quotes on the left, this is that bottom quote where the team was able to explore the space and achieve a 50x improvement in time to equilibrium ensemble simulation versus GPU alone. So once again, building a system that delivers acceleration of AI models at scale here allowed the team to couple that with an HPC solution and achieve an equilibrium solution faster. So I'm going to end this section a little bit early and deliver some time back. I'm also happy to answer a couple of questions, but at Cerebras, AI for science is really at our foundations. As we look across both commercial and government and public customers doing related scientific research, we see massive interest in larger and larger scale models, up to say hundreds or billions or even trillions of parameters. We also see growing interest in AI at its intersection with HPC and in the use of not just large language models, but large multimodal models for scientific research. Traditional systems are suitable for this work, but they're really not optimized for this work. Our system was built for large-scale AI of this nature from the ground up to eliminate the challenges associated with clustering and distributing large workloads over traditional machines and building a machine that can deliver throughput for even the largest models with simple data parallel scaling only. Our mission is really to become the de facto platform for the kind of work that we think you're doing, and we're eager to learn more. Our focus right now, as you can guess from the previous slides, is large language models for scientific AI, whether your language is human language text, say in scientific literature, or other scientific data that is structured as a sequence, like genetic or epigenetic data. And our future focus in the near future is enabling features through our software that will allow users to train not just large language models, but also large multimodal models and build surrogate models, surrogate AI models for physics, really to fundamentally accelerate researchers' ability to ideate and innovate at scale. So we're really looking forward to learning more about the kinds of projects that you and your teams are working on through the course of this workshop. And I really appreciate the opportunity to be a part of ALCF, and we hope we get the chance to work together.
Thank you.
Sorry, I'm early. There's a last question from Jason that I see. Has Cerebras compute been applied to more general purpose problems like simulation? Yeah, actually we have. We can probably share a couple of publications offline, Jason, but as you might be thinking, if one considers our primary processor, the wafer scale engine, as effectively a large-scale linear algebra accelerator, that's really what it is, 850,000 cores built to accelerate sparse linear algebra. Right? If you start to think about the wafer scale engine as a big linear algebra accelerator, then you might ask yourself, well, what about using this thing for traditional HPC workloads or algorithms common to modeling and simulation? We have multiple ongoing collaborations in that space. Customers have used our machine for example, to accelerate computational fluid dynamics, and also accelerate some traditional HPC algorithms that are used for seismic data processing for energy modeling. We have a lower level software development kit that our team has developed and shared under a private beta with select collaborators for this purpose. So we're happy to chat a little bit more about that offline and share some of those publications if those are of interest to you and your team.